Our next presentation is from Mr. Andy Rayner with Nevion, a Sony business unit. And he's going to be talking about compression in IP production. Wrap us up. Thank you very much.
Thank you very much, Wes. Good afternoon. Good to be back again. And take you through this topic. Just as I said yesterday, just a little bit of news from last time I was speaking at the IP Showcase in September. It was just the day after the death of Queen Elizabeth, and in less than 2 weeks, in fact, I've been having meetings today planning how we actually do coverage of the coronation of King Charles. So there you go, that's the hot news from the UK. Also, a little plug for you, I'm going to be here twice tomorrow. At midday, 12:30, I'm going to be doing some case studies on 6 different mini case studies, just like 3 or 4 minutes each, of deployments of distributed production. So distributed IP production in very different countries, different types of application, different models. And then tomorrow afternoon, with my friend in the industry, John Mayotte, we're going to be doing a workshop on timing in IP production, which is just back round there, around the other side. So that's at 4:30 tomorrow afternoon. So do join us for either of them if you're able to. Okay, so moving back to the topic of today, timing in IP production. This is a slide I've been using a lot in the last few months because this actually demonstrates the true value of the IP production transformation. The original turning to IP was little more than converting SDI into 10 gig fibers instead, which gave you a format agnostic interface. So you were then agnostic to the spatial and temporal resolution, etc., but it didn't give you much other benefit. However, once we look at this picture here and we think about that multi-location where we can actually have the people wherever we want, then we can have any location we want to be involved in, and we can actually locate our processing in any location. That suddenly actually is transformational in terms of the way you work, the workflow works. And also, you'll see my little sustainability logo over there. What we're enabling is actually a far more sustainable, lower carbon approach to the way we actually do IP production if we use some of these tools. And I'm going to unpack the compression bit alongside that in a minute. But the other generic slide I wanted to use at the top, which is I think very useful, is this slide about the different topologies of distributed production that we're actually using. So we did some work a couple of years ago now with the DPP, trying to characterize the ways that distributed production is architected. And what you see there is the 5 models we came up with. The dark blue is the acquisition location, the yellow is the processing and storage location, and the orange is the control location. And as an example, that remote controlled one, the second one down, was a key element that was actually used a lot in the pandemic. People were able to do lots of actually remote control, so low bandwidth control into there. But all of these models are actually being significant use now in deployments that we've been involved in. And I've actually created over this side some additional models of slightly additional different topologies that we've actually seen and actually used in implementation for customers. So bear those in mind as we start thinking about the compression side. A different way of looking at that, and I just want to highlight the 5G connectivity because that's actually key as we start to consider compression as well. We're looking at, largely speaking, although not exclusively, those long haul interconnects where compression is actually extremely important. So there's the headline, there's the overview. What I want us to dive into now is why would we want to compress video? So there are 3 main threads of why we would want to do video compression. The first one is a storage-centric requirement. So first of all, the cost of storage. If we actually can compress a video, then we actually need proportionally less storage, and that also allows us to scale our storage better. So that's one one reason, and many devices that store video, specifically video data, actually use compression for that. The middle one there, interface costs. So the cost of actual interfacing and the connect is actually can be quite significant. Also in the middle there, public cloud I/O. At the moment, it is impossible to get in and out of public cloud infrastructure with uncompressed video, unless you're standard definition. Well, we can probably do that. But in terms of HD or UHD, it's just a no-go. So there's a need to compress to actually get in and out of cloud storage. And then the most obvious one, and the one that actually drives most of the situations that we're looking at, is the cost of bandwidth and the limitations of bandwidth. So when I say the cost of bandwidth, that's actually very different in different territories globally, and I'm going to give a couple examples there. But also there are some places where it's just not only the cost, but the actual availability of high bandwidth is very, very minimal. So that's a driver to consider using compression. Okay, so those are some of the reasons why we may want to look at doing it. Just to want to remind you that compression has been around a very long time, because when we started developing television, when I say we, I wasn't quite alive then, 90 years ago, there was a thought that actually we need to create a certain refresh rate for the human psychovisual system to cope. So because of the bandwidths available, we actually developed interlace. It was the first compression, because what it said is, okay, I need so many lines of resolution in my image, but I've only got so much effectively available bandwidth in my transport system, my analog transport system as it was then. So what I'm going to do is I'm going to send half the picture then, and then later half the picture. So there is a faster temporal update, but actually I'm halving the bandwidth. So compression in some form has been around for a long time, and of course we're still dealing with the legacy of interlace as a compression in many systems even today. A quick look about what happens, what are the mechanisms by which we do compression. So fundamentally, this is a very, very, very generic diagram of how we actually compress something. So we get our source linear uncompressed video on the left-hand side of that picture. We do some kind of transform, and we're going to talk very briefly about DCT and wavelet transforms in a minute. Then what we do is we do quantize. So this is where we actually say, okay, I'm going to actually break up. I'm going to make some approximations, if you like, to the data to actually reduce the amount of data I've got. We then have depending on the type of compression we're doing, and we're going to come onto that in a minute, we then have this feedback loop where we actually do the inverse of that transform on the quantize, and then we actually do some motion estimation. So if we're doing what I call temporal compression, we actually predict where the movement of the picture is to actually allow us to do that even more efficiently. Then we subtract that from what's happening. And then on the right-hand side, there's what we call entropy encoding. So this is actually processing either losslessly or lossily the data that we've ended up with as a result of that transform to actually get our final flow. And as an observation, if we're actually going for a constant quality encode, inherently the flow of data that we create on the egress of our compression is variable in bit rate, because depending on the motion or the complexity of the image, we're going to have more or less data generated. So any individual video frame has a degree of entropy, and then obviously there's the motion element as well. So if there's more motion in a temporal compression system, there's inherently more entropy as we actually move between video frames. So inherently what we create is a variable bit rate flow. Most, and I'm going to come on to this in a minute, most of the way we consume or use that is actually saying we actually need or desire a constant bit rate flow to actually use in the compressed domain. So what we do is we play tricks in varying some of the mechanisms in this loop of compression to adapt the quantizer, adapt the entropy encoding to actually give us a constant bit rate of the compressed video flow. We'll come back to that in a minute. So some applications that are driving it. We've talked about available bandwidth. One thing that I'm doing a lot of work with at the moment, which is an interesting use case, is 5G. Now, I don't know how many of you heard the holy grail, the big high promises that 5G was going to deliver. The headline data figure that came out originally in 5G was 10 gigabits per second of data. That was the number that was associated. And everyone was saying, wow, we can even do uncompressed video over 5G. The reality is much, 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 much lower. So probably, realistically, we've got maybe a usable couple of 100 megabits per second of data that we can actually use to transfer in a video system. So if you do the mathematics, and we'll come on to that again in a minute, we actually do need to do some compression to be able to handle video within 5G infrastructure. But we'll unpack that in a minute. Just jumping back to what I was talking about, our consumption of inherently VBR compression in a CBR environment. Everything that a lot of what we do is in our world of compressed and uncompressed data is constant bit rate. So 2022-6, SDI was constant bit rate. You've got 270 meg, 1.5 gig, 3 gig, and so on. 2022-2, that's a constant bit rate transport stream. So typically that's actually carrying compressed video data that's had that dynamic quantization applied to give us constant bit rate in the flow. 2110, largely speaking, is linear, although -22, as we're going to come and look on in a minute, is compressed. But even that compressed is actually mandated as a CBR flow. And then obviously the audio flows themselves in the uncompressed PCM domain, as pretty well we're all using, are all uncompressed and are all constant bit rate. I'm not going to go through more of this in any detail now. Just want to use one example for some tools that you may be using in NDI. Despite being a very, very massive 2110 proponent, in my day job, I actually am an NDI user at other points in my life. And it's interesting to observe that if you look at natively the native normal NDI output of a system, it is incredibly VBR. And that actually can cause challenges in some systems, because you can actually have a data flow out of an NDI interface that may be sub 1 megabit per second at one moment, and then maybe up to 150 megabits per second within a few video frames. So there is a very, very high entropy, and if you actually look at the behavior of that in association with other flows, there can be some challenges, which is why in many other systems, and indeed some of the other NDI systems, it's actually converted to constant bit rate information. Coming back to the cost of bandwidth and interfacing. So one thing that's happened during my working life is that the cost of bandwidth and available bandwidth has actually gone up massively. So I think when I started working in the telco sector, 140 megabits per second was a massive bandwidth that was available, and you look at the kind of interfaces per interface capacity that's available now, and the cost of that has come down, but is actually very different in different territories. So there is high bandwidth available, and the general premise I think that most of us apply both within a facility and in wide area network is let's compress as little as possible, and we'll come on to that in a minute. In fact, a friend of mine that used to work for ITV back last century, Neil Brydon, once said to me, you only have one chance to make a first compression. And that's very true, and one of the reasons we are very, very cautious about a compression, using compression in broadcast, is because there are inevitably multiple compressions that are happening within a broadcast chain, between the camera and the end viewer, and any of those downstream compressions can be made significantly worse, potentially, by the upstream compression that's being deployed. So it's very, very important that we consider not only a single hop compression that we're using, but also the aggregate impact of multiple concatenated compressions, which is why if you look at some different compression tools, they're advertised as being multi-generational with very little degradation, because that's absolutely vital to the end-to-end system. But if you look at typically that last compression hop in a broadcast production, the DTH, the getting to the end consumer, that usually is incredibly aggressive compression. You're trying to actually squeeze very, very aggressively into a broadband delivery to the home, or a multiplex on a satellite or a terrestrial system, or getting to a mobile phone. Any of those they're trying to make maximize, so you're squeezing it very, very hard, which is why you want the chain upstream of that to be as pristine as possible. Just jumping back to the not compressing when we don't need to. Almost, I think, 8 years ago in the UK, a network that we were involved in for the Premier League football was actually was very significantly was deploying very, very high capacity uncompressed connectivity to actually allow the most pristine quality. So typically I think each stadium could easily handle 40 uncompressed HDSDI feeds as standard delivery to actually get back there, which obviously made the transition to remote production very straightforward as well. And obviously the only thing you need to deal with then is latency, the speed of light in fiber, which is, for every 1 millisecond you can go 200 kilometers. So for most national deployments, you're only talking about a very small handful of milliseconds in there. So let's look at different types of compression. So we've talked about uncompressed at the top there. I've alluded to different compression techniques, and we've got two other families of compression here. We've got what I call mezzanine compression or intraframe compression, which typically is the order of 10 to 1. And that's all that's doing is actually looking at each individual image and actually compressing it within the image. We then move on to what I call temporal compression, and if you remember that motion compensation feedback loop in my first diagram of compression, these compression techniques actually not only compress within the image, but then they also say, okay, what is the difference between the delta between this image and the next one, both objectively and with any movement that you can track using motion vectors, to actually say, let's exploit that motion as well, and we're going to allow for the movement before we actually do the final compression. And typically we can achieve maybe almost up to another order of magnitude of compression, depending on how pristine you want to be there. So we can do 1 or 2 orders of magnitude of compression of the native uncompressed flow by using different compression tools. Shown here, these two compression technologies here are both wavelet, and we'll talk about that a little bit later if we have time. And these other ones down here are typically DCT based. They're both the transforms that are used. So many of you have probably seen this compression triangle. We're looking at this in more detail, and we'll come back to it in a minute, but there's always been a trade-off between the quality of the that you want to achieve, the latency that you're prepared to tolerate, and the bandwidth that's available to you. And there was some friends of mine in Interpix created a more complex version of this, which I think helps to show this in more detail here. Hopefully you can see that from where you are. But we're looking here, what we're trying to do is look at uncompressed. So those green dots at the top, that green line there is uncompressed. So it's the lowest possible latency, because we're not doing any compression. It's the lowest possible complexity because we're not doing any processing, so there's no grunt involved in doing that. And it's the highest possible quality. So those 3 metrics are met perfectly by uncompressed. We've then got a variety of other compression options. So if we look to what I call that aggressive temporal compression that can give us those highest compression ratios, it's the red ones at the bottom there. So typically it's by no means the lowest latency, the lowest complexity, or the highest quality because of what we're doing there, but we're actually achieving the highest compression ratios, and therefore we're actually enabling connectivity in some environments. We've then got JPEG XS here. And I'm going to come on to just talking about that because that is becoming, I think, the de facto compression transport in the mezzanine space for doing IP production. And it's not the lowest latency, but it's very low. It's not the lowest complexity, but it's pretty low. It's not the highest quality, but it's pretty high. But also, it doesn't have that higher compression ratio. Typically we're using 8 to 1 maybe as a finger in the air, but it has also been optimized for use, JPEG XS, on multiple platforms, not just FPGA but GPU and real estate. So thinking about those compressions, let's now look at those options in terms of what they mean in the time domain, how much cost we have for them. So we have JPEG 2000, which has been around, well, for 20 years now, quite amazingly, and we've been using that on and off. So typically, we're looking at maybe the order of 3 video frames plus some buffering to actually achieve that. That's full frame JPEG 2000. So this is looking specifically at these Mezzanine ones. We then came up with JPEG 2000 ultra low latency. And what was that doing? That's actually saying, rather than compressing the whole image and then sending it, which of course incurs latency in its own right, because you've got to wait for the whole image to arrive before you can then apply the transformations and then send off, and then the same with the reconstruction at the far end. What we said was we can create stripes, because we've inherited our raster scan that we've been living with for the last, so we serially deliver from the top left of the picture down to the bottom. So if we say, if the first third, once I've got the first third of my picture, I can actually compress that and send it, let the next third arrive, and I can achieve effectively a pro rata reduction in the latency incurred by doing that striping. And then JPEG XS effectively is just, it's not just because there's been some improvements in the coding algorithms, but it effectively is just saying, let's micro stripe it now. Let's not split it into thirds or ninths. Let's split it into just maybe 8 or 16 lines of video and compress those and send those. And by doing that, the actual compression of JPEG XS, which is why it's very attractive in the production environment, itself is sub-millisecond for the encode and decode cycle. So that makes it very, 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 very low latency. And in fact, the IP buffering you're going to do around it is probably more dominant than the actual compression itself. So I think probably I've actually already told you everything about this, the journey from JPEG 2000 to XS as we've gone through there. A few facts about JPEG XS here. I think the key message is it's very, very flexible, and it can be used for a big variety of applications, not just broadcast video. So when we started developing ST2110, there was no concept that we would want to use video compression. We defined -20 as linear, or RFC 4175 linear uncompressed video. We defined linear uncompressed audio as -30, and then the -40 for the ancillary data. But if you look on the second row there, on the very left-hand side, and I just highlight it there for you, we actually defined later in the day, this came to the party late, -22, which was compressed video, because we suddenly realized that there are specifically reasons why we want to do video compression. And one of the key drivers for that, if you think back to my 3Ps diagram at the beginning, is if we're actually wanting to be location agnostic, we want to long haul our production and stay in a 2110 essence environment, then we actually potentially need to do this, because although the cost of bandwidth and connectivity within a facility is pretty low, if we're going long haul, either nationally or even more so internationally, we do need to do compression. But if we want to stay in the essence world, that's what -22 has served. And thinking back to that constant bit rate, variable bit rate, one of the things that we do very carefully in 2110 in general, because it's UDP data and is therefore inherently fragile, is we have packet pacing defined in 2110-21, and that packet pacing also needs to be applied to the compressed video data carried in -22 as well. So what are the typical rates that we're using in broadcast production when we're doing this lightweight Mezzanine XS compression? These are just some typical bit rates that we're assigning to use for the compression. It's fair to say that probably if you compare JPEG XS with JPEG 2000, you need a little bit more bandwidth for JPEG XS for the same visually lossless level, simply because there is less efficiency if you're only compressing tiny stripes of the data. So in terms of trusting JPEG XS, I was actually amazed when I looked at this slide earlier today when I was thinking about it. It's well over 3 years now since we did our first JPEG XS deployment. In fact, the standard wasn't even finished when we did the first deployment, but we actually started using it in a pan-European project. And actually, it's actually been highly successful, and the XS is used and is being used significantly in Angra in many places now, but for the international connectivity to reduce the bandwidth bandwidth there. And in terms of the application, just to show you how that looks, this is it. So we're going from one location there, we're carrying the JPEG XS dual and diverse, using 2022-7 to actually carry that across a wide area network, and then at the other end. Now, for those that have been involved in compression for many years, most of you will think of actually having an SDI cable at one side of an engine and then some compressed output at the other side. But most of the compression that we're now deploying is typically just IP to IP. So we're actually, we've got an IP interface coming in as 2110-20, and then we're pushing it back out as 2110-22, and vice versa. So actually, it's just an inline IP processing resource now, rather than being something that's converting us from the world of SDI. Another application space where compression is needed, as I alluded to previously, is going in and out of public cloud infrastructure. The cost of bandwidth or the availability of high bandwidth is precious. A lot of applications are using what I call aggressive compression, temporal compression, to get in and out of cloud, just because only low bandwidths are available. But one of the pieces of work that's being done in the VSF GCCG at the moment is looking at the different tools, the different ways for different qualities of getting in and out of cloud infrastructure. I'm not expecting you to take this diagram in. I don't usually go for complex diagrams, but it's just worth pointing out here that what we're looking at here for what we call pristine cloud I/O is actually a essence-based infrastructure where we're carrying -22, -30 and -40 flows, and we're using JPEG XS compression for them. You'll have seen probably the publication of TR08 and TR07 by the VSF in the last few months. TR08 is what I'm describing as -22. We've actually been doing effectively TR08 for the last 3 years, very, very effectively. And that's effectively used when we want to interconnect 2110 systems, because it's an essence-based and it maintains the essence-based workflow. The TR07 is an alternative variant of how to transport the compressed JPEG XS stream alongside and with the audio and other data using transport stream. It doesn't have the same clocking requirements, and if you want to look back at my presentation from yesterday online, please do so, because I cover a little bit about that. But just to say, these two recommendations are both ways of carrying JPEG XS, but in different circumstances. So drawing to a close here, just like to say, hopefully that's been of some value. And if you want to pop over, when I say pop, it's a long walk from here. It's right the other side of Central Hall. But we've got both JPEG XS and some new innovated high efficiency HEVC available, that you can see how it looks, and the latencies available in XS and H.265. And one of the things about the demo that's very impressive is there are some various tricks that you can play with HEVC compression, with this temporal compression, to actually get the bit rate down, but also have very low latency. So you can see sub 40 millisecond encode decode, whilst maintaining very, very high compression ratio in temporal compression for HEVC. So do come over if you'd like to see that. Okay, I'm drawing to a close. Thank you for watching, or thank you for being here. And I'd like to invite you, as always, if you want to come over, I'll get you a nice cup of tea, or if you're ever in the UK and fancy a nice cup of tea, do come and join me. Thank you very much.
Thank you, Andy. Do we have any questions? Anybody want to get a little bit more information while he's here? Okay, because he can be kind of hard to track down sometimes.
And it's a long walk over to that booth.
It is. Go ahead. Here.
The last slide between Essence and one,
Yes.
That I didn't get the difference between TR08 and TR07.
Okay, so the way they're transported is TR08 is defining what we do in SMPTE 2110-22, and it's carrying just the video data, the compressed video data, specifically the JPEG XS compressed video data, as a flow, as an essence flow. So it's very analogous to -20, the uncompressed video, but just being carried as a compressed flow. What TR07 is doing is fitting that compressed video alongside compressed audio, alongside alongside ancillary data as well, and wrapping it in a transport stream, a traditional 2022-2 transport stream, and carrying it as a single transport stream, which means it's what I call a composite flow, because it's actually got that flow you're handing off has actually got the video and the audio and the ancillary data contained in one pipe, in one IP flow. Also, the way you actually do timing is different, or it can be different, because inherently TR07 is and transport stream clock recovery is an adaptive forward clocking recovery, so you don't necessarily need to have the same timing domain as you would in a 2110 production at both ends of the system. So I can unpack that, or you can watch the video from yesterday where I went through that in a bit more detail.
So the question is, where can we see the videos? So the videos will be posted within a month or two, and the IP Showcase website. You'll see them all posted. But you want to see it over here. You want to see Tina to get your badge scanned, and she'll send you the information about it, okay? As well as the presentation.
In fact,
Tina. Oh,
here
she came around.
is.
That's right. There we go.